Okay, so I am going to be talking about basically synthesizing, as Vita mentioned, synthesizing some work that I was involved in, as well as some other work that has been going on more recently in the Northern Rockies on the US side of the border. So I'm always careful to say the US Northern Rockies, realizing that the Rockies extend well north of our border, despite some of the maps and what they would have you believe here. But as Vita mentioned, my name is Brian Harvey. I'm an assistant professor at the University of Washington, and currently doing lots of work out here in the Cascades, on both sides of the Cascades, and fire and forest disturbance. But I did my PhD research at the University of Wisconsin, working with Monica Turner. And she and her colleagues have been working in the greater Yellowstone area for a long time. And so I was fortunate enough to do a lot of my PhD research in greater Yellowstone and also in Glacier National Park and in the areas in between the two. And so certainly overlapping with the crown of the continent location, but I'm going to be talking about some trends more broadly in the US Northern Rockies as well. Before I get started, I want to acknowledge lots of collaborators and funders that have been involved in pieces of this work, at least the pieces that I've been involved in. I'm going to be synthesizing some additional work by other researchers out there, but I've had the pleasure to work with the folks that you see here, as well as have this work has all been supported by many different groups and agencies here, and would not be possible without a very large collaborative effort and lots of support from a range of different partners and supporters. So when we are thinking about forests, fire, and resilience, I think about the US Northern Rockies as in some ways a pretty important outdoor laboratory to think about these questions. And as many of you all know, in the region from Yellowstone up to the Yukon, we've got opportunities to understand these systems in ways that we can't in other areas because of how our human footprint on the landscape. And so we've got very large areas where fire is playing the role that it has historically in these ecosystems in many ways. And for the US Northern Rockies, oftentimes the 1988 Yellowstone fires is used as, in some ways, a benchmark of large fire events and resilience to those fire events. And we know from that event, as well as in the paleo record, that forests in the Northern Rockies have been resilient to fire, and even very large and severe fires. So just as a quick reminder of the 1988 Yellowstone fires, it burned in total more than a third of Yellowstone National Park, as well as over 1 million acres inside and outside of the park. And that fire was very large, but extremely heterogeneous in its burn severity pattern, as we see here in the photograph taken from a helicopter looking down on that burn mosaic shortly after the 1988 Yellowstone fire. So very large, very severe fire. It was followed by conditions that were relatively kind and conducive to post-fire regeneration. And for many of you who have been to Yellowstone National Park or similar post-fire landscapes up and down the Rockies, the resilience of forests to fire and their capacity to recover is on full display. And I love these shots of Yellowstone because these signs that say naturally reseeded by wildfire in 1988, many of the folks in Yellowstone who visit, if those signs weren't there, they wouldn't realize that they're staring at the same forests that were in this blackened landscape that was all over the news several decades ago. This thing has bounced back like crazy, and it has been extremely resilient, right? And so it's just one example of many that we can point to throughout the historical record of how forests in this region are extraordinarily resilient to fire, and even very large and severe fires. However, over the last several decades, things have been changing quite a bit. And as the climate is getting warmer, in this case, some work by Phil Higuera and John Abotsoglu, highlighting the trends in summer vapor pressure deficit. So that's the black line that we're seeing here. As that is increasing and the climate is getting warmer and drier, correspondingly fire activity is increasing. And so we're looking at thousands of hectares of burned area in the red lines there. And that tracks very well with something like vapor pressure deficit and many other climate variables. And so that has led to lots and lots and lots of questions about how forests are responding to these changes in fire activity, as well as the changes to the climate itself. And are forests going to continue to be resilient in the future? And so many questions that are arising and sort of leading into the topics that Vita had asked me to synthesize in this talk today. Folks are curious, understandably, about are fires becoming more severe as we're seeing this increase in fire activity. And so I love this picture because it highlights the fact, many of you might recognize this very location, but it highlights the fact that I did not have a smartphone that I could take a nice panoramic shot when I took this picture. This was during my dissertation work. This is in Glacier National Park in the Going to the Sun Road. And this is the Trapper Fire at a lookout right at a big bend in the road here. And I had to take 3 photographs with my old school camera here to actually capture the size of this large stand replacing patch, because it was so large, so long, and so wide. And so there's lots of concern and questions about are stand replacing patches, or these really severe patches of fire becoming more common and larger in recent fires than they were in historical fires. Also, lots and lots and lots of questions about are forests coming back after fire the way they used to, right? And so the way they used to, I think we can sort of use colloquially for, again, forests have been resilient to large and severe fires in the past, but are they going to continue to be as the climate continues to warm? And most importantly, that post-fire climate window, is that changing in ways that are going to erode resilience or capacity to bounce back for these forests? And then finally, the question about reburns. So in many fire regimes up and down the Northern Rockies, the historical fire return interval for a given patch of forest was on average, you know, a century or several centuries. But we're starting to see areas reburn at a higher frequency than at least the average conditions would suggest. And so what are the causes of these reburns and what are the consequences for forest resilience is another big question that's on a lot of folks' minds. And so for today, again, covering some regional trends in these 3 questions or key focal areas here. So let's start with the burn severity question. So as we have seen this increase in burns or in total area burned, correspondingly, we are seeing increases in severely burned area as well. And so this is some work by Sean Parks and John Abotsoglu that came out recently. And they looked at across the Western United States in several different ecoregions, these trends to ask, as area burned is increasing, is area burned severely increasing, both in aggregate total amount as well as the proportion of that that's burning at high severity. And I'm just pulling out 2 figures that I kind of modified from the figure in the paper here to highlight the Northern Mountains region. So it covers a lot of what we're talking about in the Northern Rockies, though it does expand a little bit into some additional neighboring regions. So it's not exactly the same Northern Rockies region that I'll be talking about shortly here, but the key takeaway that they found is many regions, and highlighted here, the Northern Rocky Mountain region, there is a statistically significant increase in the total area burned, as well as the total high severity area burned. And that's what we're seeing, those 2 trends on the upper half of this figure here in this graph. And in addition to that, the average level of burn severity. So they characterize this by the composite burn index, or CBI, which is something that is used very commonly to characterize burn severity in the field, and that's something that can be related to satellite indices of burn severity to be able to wall map burn severity across burn landscapes. And they saw that the average level of burn severity, or in other words, the average CBI value, has also statistically increased over this time period. And so all three of these metrics are increasing over the time period of the mid-1980s until now. So that gives us a little bit of an idea of how severity is changing. So that's sort of at an aggregate level of severity. One curious question that I know lots of folks are interested in, and one of the things that we tackled in a recent or a past paper here is the heterogeneity of that severity changing. So again, the Yellowstone fires were very severe, but that was distributed in a mosaic and very heterogeneous manner of high severity interlaced with lower severity and unburned patches throughout this landscape. And so has that been changing over time as we've been seeing this increase in aggregate level of severity as well? And this is something that I tackled as part of my dissertation work in a paper that came out in 2016 in Landscape Ecology. And so some of the trends that we might expect over time, if we were thinking about are fires becoming more homogeneous in their severity patterns over time, is displayed here in this kind of cartoony figure here. And so one way to characterize this is we could look at the proportion of stand replacing fire. And so stand replacing being areas where greater than 90% of the basal area of trees was killed by fire. And we could characterize that as literally just, is the proportion that is stand replacing increasing over time? Is the configuration of that high severity fire also changing over time, in that we're going from an increase in mean patch size over time from many smaller patches to fewer larger patches of high severity or stand replacing fire? Are those patches becoming simpler in shape? So even if these things weren't changing, we could be seeing patches go from lots of edge and very complex shapes to simpler shaped patches. And all of these metrics would lead into a really key piece of information that we'd want to know is the core area or area within those stand replacing patches that is really far from seed sources, which we defined as 150 meters or greater from seed sources, sort of expanding or exceeding the reliable dispersal capacity of many of the conifers. Is that core area increasing over time? And so what we did in this study is we looked at all of the fires that had burned from 1984 through 2010 at this point in time, to ask, are we seeing a change in the configuration of this high severity or stand replacing fire? And the key takeaways from this study is that we did see some trends. They weren't extraordinarily strong trends in the change of the landscape patterns of burn severity, but we did see an increase in proportion of fires burning at high severity from about 22% of an average fire at the beginning of the time period burning at stand replacing to 27% at the later part of the time period. So in terms of an actual percent increase, that is about a 23rd or almost a quarter increase in the proportion of an average or given fire that is burning at stand replacing over this time period. We also saw that the configuration of that stand replacing fire was trending towards slightly more homogeneous burn severity patterns. So an increase in the patch size, a decrease in the patch shape complexity, or patches becoming more simpler in the recent fires. And again, the key metric here is more total core area that is far from seed sources in these fires that have been happening later in the time period here. So trends in burn severity overall tell us that one thing that's really important to remember is large fires are still very heterogeneous, right? So over the record that we looked at in the Northern Rockies, the 1988 Yellowstone fires was actually still the most homogeneous or blobby in terms of big, simple shaped patch sizes fire that we've seen here. So large fires that we're seeing today are still very heterogeneous if we consider the 1988 Yellowstone fires heterogeneous, which lots of work has demonstrated they are. So large fires are heterogeneous, but as burned area is increasing, we're seeing a corresponding increase in the proportion and total area burned as standard placing fire, and the patterns, the spatial configuration of that high severity fire is starting to trend more homogeneous over time in any given fire that you were to pull out of the sample of more than 1,000 fires that have now happened over that time period in the Northern Rockies region, Northern US Rockies region. Okay, so that's a quick overview of some trends in burn severity. Now switching a little bit to tree regeneration, and specifically focusing not only on tree regeneration, but post-fire tree regeneration. And I would say even a critical window or place to look at post-fire tree regeneration is after standard placing fires. So this is a really critical but fragile stage for a forest, because after a standard placing fire, you're basically passing the torch over to the next generation. Obviously, a tree that is in many cases several hundred years old might be able to weather climate conditions, and there's a lot of inertia in that tree and in that forest stand that's several hundred years old that becomes very fragile when we're talking about 1 or 2 or 3 year old seedlings following a fire that are going to be perhaps much more vulnerable to drought conditions. And sorry, the chat thing popped up right in the middle of my slide. To post-fire drought conditions, right? You can imagine this little post-fire Douglas fir seedling is going to be much more vulnerable to a prolonged 3-year drought than its several hundred-year-old predecessor prior to the fire might have been. And so to test this, one way that we've done this is a regional field survey, where we basically went into fires that had burned between 1994 and 2003. And that period of time was chosen because we sampled these fires in 2013. So we wanted to give at least 10 years post-fire for post-fire seedlings to establish. And then what we did is we characterized the rate of annual post-fire seedling establishment by taking the time since fire, the number of seedlings that were there, and coming up with a normalized post-fire seedling density in fires that occurred over this time period. And this was work that largely was inside of Glacier National Park and Yellowstone National Park. So 2 sort of focal subregions within the Northern Rockies. And in those fires, we focused on standard placing patches where there was near or total overstory mortality from the preceding fire. And we intentionally sampled fires that covered a range of post-fire climate conditions, as well as plots that covered a range of distance to nearest seed source. So we could get kind of at 2 questions. What is the effect of those large burn patches in terms of distance to nearest seed source on post-fire seedling establishment? So that's kind of the seed delivery piece. And then once seeds are there, what's the effect of the post-fire climate conditions? And what we looked at was a period of time of 3 years following each of these fires. What was the cumulative moisture deficit during that time period? And we use that to characterize post-fire drought severity. And the key takeaway from this work was that post-fire seedling establishment, not surprisingly, but important to quantify this, declines sharply with post-fire drought severity and also burn patch size or distance to seed source. And so on the left-hand side here, these 3 bars here are showing the standardized effect sizes of 3 things that relate to what we focused in on this study. One is the regen, and this is essentially saying post-fire seedling density was much greater in Glacier National Park than it was in Yellowstone National Park. And so we saw some regional gradient in, as you went farther north, there's less moisture deficit in general in Glacier than there is in Yellowstone, and there was greater post-fire seedling density in Glacier than there was in Yellowstone. So a decrease in seedling density as you went further south. In any given location, fires that were followed by post-fire drought had lower seedling density. So post-fire drought severity had a negative effect on seedling density, and distance to seed source had an important and negative effect on seedling density. And so this pictorial version is if you picked plots that were in these 4 quadrants of our questions, near a seed source, far from a seed source, going from left to right, and followed by low post-fire drought severity in the 3 years following fire, or high post-fire drought severity in the 3 years following fire, and picked plots out of those 3 quadrants. These were the average values and a glimpse of what those stands look like. So clearly, if you're near a seed source and you're followed by nice conducive climate conditions following a fire, you have very high seedling density. And that's a scene familiar to many of us, where you've got larch or lodgepole pine that's so dense you've got to sort of peel away the rows of trees to be able to walk through it. But an order of magnitude or greater decrease in seedling density as you go from near a seed source to far from a seed source out in the middle of these patches. And then in both situations of near a seed source or far from a seed source, if you went from low post-fire drought severity to high post-fire drought severity, another order of magnitude or 2 decrease in seedling densities. And so I want to just bring our focus on this quadrant right here, which essentially tells us a possible glimpse into the future of what post-fire regeneration may look like in areas that are far from a seed source, as well as areas where fire was followed by strong post-fire drought conditions, where the post-fire seedling recovery for this forest is much, much, much slower than in areas that are either near a seed source, so in a smaller burn patch, or followed by relatively mild climate conditions. And so this, many modeling studies have now been done to suggest that these are the conditions that we may expect in the future. Less seed source available because of larger burn patches or younger forests burning that have less seed available to begin with, and that are followed by warm, dry conditions. At the lower tree line, some work that was led by Dan Donato in Yellowstone, looking at Douglas fir recruitment following the 1988 Yellowstone fires, suggests that in that lower elevation forest in Yellowstone, so Douglas fir forms the lower elevation tree line in similar ways that ponderosa pine does throughout the rest of the Rockies, but ponderosa pine is absent throughout most of the greater Yellowstone ecosystem. Douglas fir instead forms that lower tree line species, and when you had standard placing fire that was in mesic locations and far from that lower ecotone, or in other words, sort of more comfortably in the zone of Douglas fir distribution in the area, post-fire seedling regeneration was pretty abundant following the 1988 Yellowstone fires. However, standard placing fire in the 88 Yellowstone fires at the dry topographic locations and near that lower forest ecotone, many locations today still do not have any measurable post-fire seedling regeneration. And so there is a suggestion that unless these areas continue to have some sort of a seed source coming into them, these areas could be where there's potential transition from forest to non-forest following a fire like the 1988 Yellowstone fires. And this is a trend that led Camille Stevens-Ruman to pool together much of many of our collaborators' data across the Rockies region in the US to look at, is this a trend that we're seeing across a wider range of forests and post-fire climate conditions? And so similar kind of approach that what we took in the Yellowstone and glacier comparison here, but as you can see, Camille was able to pool together plots from lots of different studies and look at over this time period, what is the effect of post-fire tree regeneration, or sorry, of post-fire climate conditions of that 3-year window following fire on tree regeneration over a much wider range of gradient space here. And so You can see in this this figure here, these were the fire years that were included in this study, and the annual water deficit that is following these fire years is continuing to increase in terms of increased drought severity following fires in this later part of the time period. And so what that led Camille to do in this analysis is combining sites, all the sites that burned pre-2000 and all the sites that burned post-2000, because the year 2000 seemed to be a pretty important breakpoint in terms of this climate signal in the post-fire tree regeneration window. And this figure really kind of sums it up well in terms of how regionally consistent these patterns are. First, on the left-hand side, we're looking at the post-fire climate, and this is the 3-year water deficit as a z-score here, with on the left-hand side, less of a water deficit or more cool, wet conditions. On the right-hand side, warm, dry conditions with a greater water deficit. And you can see that that distribution of years shifted from the sites that were burned pre-2000 being more on the left side, or the cool, wet conditions, to sites that were burned post-2000 having on average greater, and a shift of that distribution to the right-hand side of a greater water deficit. Correspondingly, post-fire regeneration, the distribution has shifted to the left, so lower seedling densities in this later time period versus the early time period. And I would say these seedling densities we controlled for time since fire. So these are, they were all given sufficient, or the equal amount of time to look at post-fire recruitment window of seedling accumulation. And the one important thing to note here is the number of sites that had 0 post-fire tree seedlings by 10 years post-fire almost doubled from the pre-2000 sites to the post-2000 sites. Or in other words, the likelihood of tree regeneration failure following fire seems to be increasing, and that's particularly so at that lower tree line elevation where you're sort of at marginal forest conditions pre-fire already. And so summing up the tree regeneration takeaway, in subalpine mid-montane forests that we looked at in Glacier and in Yellowstone, overall tree regeneration certainly declined sharply with greater post-fire drought severity and distance to seed source, though it was pretty rare to come across a plot in any of the fires that had occurred in Yellowstone or Glacier at that point in time where there was a lack of tree regeneration. There were a few, but it was pretty rare. Whereas at that lower tree line elevation, the warm and dry areas that are near that low tree line pre-fire are where it's most likely that we have yet to see any post-fire tree regeneration in several of these studies that have looked at it. And those are areas that, you know, it's tough to tell if that's a temporary and persistent condition, or if that is in some ways, you know, over management timeframes, at least a potentially longer term conversion of forests to non-forest post-fire. Okay, so I'm going to wrap up here on some regional trends on the reburn question here in the US Northern Rockies. And so first, again, these reburns are something that are on the minds of lots of folks as we're seeing them start to occur. And so one question that is on at the forefront is, what are the drivers of these severe reburns, and what makes them more or less likely to happen? And so one thing that is important to remember, as many of us can imagine, if a severe fire happens, like we're looking at the foreground here, the likelihood of a subsequent severe fire is obviously going to be pretty low following one severe fire, because most of the available fuel has been removed by that fire. And so as many of you I'm sure know, a severe fire or a past fire buys us a little bit of time in that it limits the likelihood of reburning. And so this is some work led by Sean Parks a couple years back that looked at this idea of a hazard ratio, or the probability of a fire starting and getting going inside of a past burn perimeter or outside of a past burn perimeter. And basically, these lines are showing you the effect of time since the last fire, to where the probability of a fire starting inside of a past fire perimeter is pretty low in the early years of time since fire, and eventually gets up to a point where it has about the same likelihood or probability of burning as an area outside of that past burn perimeter, right? And so past fires certainly limit the likelihood of reburning, but those effects decay with time since fire, as we're seeing in all these curves. And the green to yellow to red colors, as we're going to the left here, show increasingly extreme weather conditions at the time of that second fire. And so as you increase those drivers of weather conditions, that effect decays as well, and it can be overridden by weather conditions. Sean and his collaborators also looked at the effect of past fires limiting the spread of a subsequent fire. So it's essentially breaching the barrier and spreading within a past fire. And so you can see on the left-hand side here, fires where the past fire, the lighter colored area here, acted as a barrier to the spread of a subsequent fire into that burned area. And so those blue lines are where that past fire was limiting. The red lines on the right-hand side are where the past fire was not limiting, or a certain proportion of the burn perimeter was basically allowed to spread well into that past fire perimeter. So they asked this question of what is that effect? What is the effect of past fires limiting the spread of subsequent fires? And basically they found that as similarly to the likelihood of fires, now we're looking at the probability of fire limiting the extent of a subsequent fire. So here, higher on this axis is a higher probability of stopping that fire from spreading. And certainly right after a fire, that probability is really high, but it does decay with time. And increasingly extreme fire weather basically shifts that curve over to the left. And so again, past fires limit the size and spread of subsequent fires, but those effects decay with time since fire, as well as under extreme weather conditions when that second fire is burning. And in a study that we did, we asked, okay, what's the in the Northern Rockies, what is the effect of past fires on limiting the severity of a subsequent fire? So now we're it's a given now in this study that fire has occurred in a past fire burn perimeter, and that it has spread, and there's substantial overlap between two fires. Now we asked the question of what's the burn severity in that subsequent fire, that second fire, compared to the first fire. And in many cases, what we saw was whether you were in subalpine forests, mid-montane forests, or the low-montane woodlands, the burn severity, or the probability of high severity fire in that second fire, if we just focused on the right-hand side here, is lower is lower in the early time periods here, right? So the probability of having two back-to-back high severity fires is pretty low in the first decade and a half following that first fire. However, you see that all of these lines cross this dotted line threshold at about somewhere around 10 to 15 years. And that dotted line threshold is basically telling us the average burn severity in that first fire. And here we're seeing that the probability of high severity fire in that second fire crosses that threshold at about 10 or 15 years. Or in other words, the limiting effect of a past fire on burn severity lasts about 10 to 15 years, after which the probability of a second high severity fire is equal to or greater than it was in that first fire. And again, this is true, past fires limit the severity of subsequent fires, but these effects decay with time since last fire and extreme burning conditions. So The standardized effects here increase with increasing interval between the fires, as well as the moisture deficit during the second fire. The greater those two things are, the higher likelihood there is of two short interval high severity fires happening. And what happens when these fires do occur? So this is the final part that I'll wrap us up on. And this was part of a study led by Monica Turner in Yellowstone National Park, when greater than 20,000 hectares in 2016 reburned parts of the 1988 Yellowstone fires, as well as parts of a 2000 fire that had occurred after the 1988 Yellowstone fires. And so essentially had reburnt 28-year-old lodgepole pine and 16-year-old lodgepole pine fires here. Now, when those fires occurred, a couple really important things happened. First, the burn severity levels that were recorded were different than what has been characterized in longer interval fires. And so if you could look at these two pictures on the left, you can imagine that a severe surface fire and a crown fire in these younger lodgepole pine forests that were less than 30 years old at the time of that second fire, these look like essentially they're analog or counterparts from long interval fires when they burn. And what we're seeing here is, you know, a miniature version of a severe surface fire or crown fire that you would expect in an older forest when it burned. But we did find other areas where we had to come up with a new burn severity class of crown fire plus, because the fire burned so severely that it actually consumed not only the stems of those post-fire regenerating trees, but also the logs on the ground and much or all of that coarse woody debris in some of these cases here. So this is a scene that I know has been recorded in the boreal forest by lots of folks who have been looking at reburns up there, and is something that we're seeing occur in some of these short interval reburns. And those ecological effects following these short interval reburns can be fairly profound. In Yellowstone, there was a 77% reduction in post-fire tree regeneration in these areas pre-fire to post-fire. So the pre-fire is essentially a proxy for what that tree regeneration was following the 1988 Yellowstone fires, though it is likely an underestimate because there had been some density-dependent thinning that may have started in those areas. So definitely a reduction in post-fire tree regeneration, and very importantly, a large reduction in above-ground carbon stocks following these reburns. As you can imagine, when that coarse woody debris as well as the tree stems are being consumed, there's much less woody carbon being left after these reburns, and those effects can be lasting and persistent. This is some work that in that paper where those stands were modeled out using the forest simulation landscape model iLand, and essentially over the next century and a half, you can see that while the live above ground carbon stocks eventually converge, the dead carbon pools in those post-fire reburns take a very long time to reaccumulate, and over this time period did not actually catch up to the long interval fires, because essentially that large coarse woody debris takes a long time to recruit and build up in these stands. So regional trends in the reburns: past fires impose constraints on the likelihood, size, and severity of subsequent high severity fire, but the effects of all three wear off by about 10 to 15 years since the last fire, and can be overridden by extreme conditions when that second fire is happening. And when short interval severe reburns do occur, the post-fire tree regeneration and carbon recovery slows in pretty important and profound ways. So what does this all mean? Wrapping it up, increases in area burned are accompanied by increases in severity, and we're seeing trends in more homogeneous spatial patterns of burn severity over this time period in the US Northern Rockies. Post-fire tree regeneration, strongly affected by climate conditions, and those effects are strongest in terms of what we're seeing in terms of changes to forests at the already marginal locations, such as the lower tree line. And those short interval reburns are starting to occur at about 10 to 15 years since the last fire. And when they do occur, the forest recovery trajectories for both tree regeneration as well as carbon recovery is much slower in those short interval, high severity reburn locations than in longer interval fires. And with that, I want to say thanks, and I don't know if we have any time for questions, but happy to take some in the discussion period later on.